Hello everyone, Dr. Data Science here to teach you data science methods and tools today, tomorrow, and beyond. In this video, we talk about parameter management in PyTorch. Once we have chosen an architecture and set our hyperparameters, we proceed to the training loop. And after training, we need these parameters in order to make future predictions. Sometimes we wish to extract these parameters for different reasons, such as debugging, diagnostics, and visualizations. And sometimes we want to also save our model and parameters so that it may be executed in another software or we use it sometime in the future. In this video, we talk about how to access parameters, how to initialize them, and how to store and load them for future use. If you find this video useful, please don't forget to subscribe to the Dr. Data Science team. To get us started, let's start with very simple case. In this case, we import torch, and then from torch, we import neural network or NN, and this is what we use for defining layers and also defining our architecture. Specifically here we are using the sequential layer, meaning that we want to put in this case 2 layers next to each other. The first one has 2 neurons, meaning that our input is 2-dimensional, and this connects to 4 neurons in the hidden layer, as you can see here. And then for the second one, that's what we have for here, that we go from 4 neurons to 1 neuron in the output layer. This is a very simple case to just show you how we can access parameters. After we define this net, which is our neural network here, if we want, we can also give some input, which is here a tensor, which is basically a set of random values in it of size 3 by 2. So this means that we have 3 examples. Each example has 2 dimensions, and therefore at the end we get 3 one-dimensional outputs. And this is the output of this net when we input x, right? So we can see that we get these 3 outputs corresponding to the 3 inputs that we have. And we talk about how to do the forward propagation before in previous lectures, but here is that how we can find information about these weights and biases that we have for these different layers. One of the most important methods that you need to know is this thing called a state underscore dictionary. So what this does is that first of all, like if you look at what we have when we define network, we have 2 layers, right? Like we have a linear layer and then we have another linear layer. And we can think of this as a list. So this would be index 0 and the second one would be index 1. So when we say net and then we index at 0 means that we are looking at the first layer. And now we use this method called a state underscore dictionary, as I tell you. And if you look at it, this gives us actually something called order dictionary. So it has 2 keys. The first one is weight, and then the second one is bias, right? Because this layer goes from 2 neurons to 4 neurons, you can see that the weight matrix is 4 by 2, right? So we have 4 rows and 2 columns. And also, because each of these neurons that we have in this hidden layer, they need a bias term. We can see that we have 4 biases, right? So we have weight and bias. And I really like this state underscore dictionary because it gives you order dictionary which contains information about both weight and bias. Now we repeat the same thing. Now instead of looking at index 0, we look at index 1. So remember that this is index 0, this one is index 1, meaning that we are looking at the second layer. And in this case, if we use again a state underscore dictionary, we get the weight and bias. And here, because we are going from 4 neurons to 1 neuron, what happens is that the weight would be this 1 by 4 sort of like array here, or tensor better to say, because we are in PyTorch. And the bias has only 1 element, right? Because we only have 1 sort of like neuron in the last layer, so this has 1 bias. So it's very much similar for any other layers that we might have here. In this simple case, we only have 2 layers, but if we had more, you can still index it and then use this state underscore dictionary. So although that we can use the state underscore dictionary that we saw, but overall we know that, for example, when we have a linear layer, right, we have weights and we have the bias terms, right? So in this case, if you want to directly access them, we can just, again, index the network that we have and then use dot weight or dot bias. And each of these attributes have different types of information assigned to them, right? So for example, for weight, we have .data, which tells us exactly what we have here. And this is exactly the same as you saw in the previous slide when we use a state underscore dictionary. And also here we can just look at the bias term, which we had like 4 elements for net 0, right? Because that's the one that goes from 2 neurons to 4 neurons. And here you can also use other sort of like attributes too. So example, for the weight and the bias, we also have the gradient. So you can say weight dot grad, grad, so to see what the gradient is. Because here I've not done any training, that if I use weight dot grad, I get none because, you know, I've never used the backward here. And so, but the point here is that you can use weight and bias, and then with data to see what exactly these parameters are. Another useful method that you can use when you have your network defined is this method called named underscore parameters. So what this gives us this name and parameter sort of like tuple. So the first item here is name that I'm showing because we have already seen the parameters for each of these sort of like different weights and biases, but you can see that each of these parameters, they have names, right? 0.weight, 0.bias, so these are for the first layer, and then we have 1.weight and 1.bias. So exactly as you can see, we have the sort of like the numbers that shows which layer they belong to, and then whether they are weight and bias. So the weight and bias are separated from each other, which is very useful because, for example, you may want to initialize them in different ways and you don't have to be worried about sort of like how to separate them. So that's the nice thing here, that the weight and bias are separated. Okay, so now let's take a look at a more complex problem here. So in this case, we want to have a nested block. So meaning that we first define block 1, which is a sequential network with a linear layer, and then rel which is rectified linear unit. What it basically does is to find the maximum of 0 and each element. So meaning that if an element is negative, then we get 0. If it's positive, we get exactly the same positive number. And then we have another linear layer and then another rel, right? So this is our block 1, that is this network. And then for block 2, what we do is that, again, we are using a sequential layer, and now we are putting 2 of these block 1s together, right? So we have this block 1, and then we have this another block 1 here. And remember that each of these also contain sort of like 4 layers, right? Like linear, rel, linear, and rel. And at the end, we create this nested network, which we have this block 2. This is block 2 that we have here. And then we add this linear layer. So what do you think here the architecture of this network is, and how we can do the sort of like the numbering? So in the next slide, we are going to see that. In this case, my recommendation is to start with printing the sort of like the network that you have. So we call this nested underscore net, and I just print this, and you can see that we get a lot of information here. So this tells us this is sequential, and then we have 0 here, and then we have 1 here, right? So the 0 corresponds to that block 2 that we have at the beginning, and you can see here immediately that this one consists of 2 blocks, right? Because that's how we created the block 2 here, right? And then at the other part, we have this 1 here, which is that linear layer that we used with 4 inputs and 1 output, right? So now with this, you can see exactly what happens. So let's say I want to, for some reason, like look at this sort of like layer. So the way that we can do the indexing is that first we index it at 0, and then we index it at 1, and remember 1 means the second item because indexing starts from 0, and then we look at the first item, which is indexed at 0. So that's why I always recommend, if you have a complex model, use print and then the name of the network. And using this information, now you can just do the indexing. This is very much similar to Python lists. If you have a nested list, right, you can always start indexing from outside until you get to the inner sort of like list that you're looking for, and that's very much similar here. And as we expected, so here it means that we are looking at the first block, right, and then the second block in that main block that we have, which is this one, and then we are looking at the first item, which is this one. And here we have both weight and bias, and in particular we are looking at weight. And in order to see exactly what data we have here, we use .data. So this way we can have exactly access to here. And as you can see, we have 4 input neurons and 8 output neurons. So that's why this weight is 8 by 4, meaning that the number of rows is equal to the number of neurons in the next layer, and the number of columns is equal to the number of neurons in that layer that we have. And this is exactly consistent with what we had before. So again, in summary, you can always have nested networks, and you can start indexing from outside to get into the inner list. Okay, so now let's talk about parameter initialization. We have these weights and biases, and as you know, in deep learning, we have to initialize these weights, and the initialization part is, in many cases, extremely important to be able to get good results at the end. And that's because, in general, gradient descent and other iterative optimization techniques are very sensitive to the initialization part. Something to keep in mind is that some of the layers, for example, when we use nn.relu or the rectified linear unit, they don't have any parameters, right? Because we just take the maximum of 0 and any input that we give to this function. So we don't have any parameters to initialize. And therefore, here when we are defining our initialization sort of like function, the first thing we are using this if statement to see if the layer is this nn.linear, right? In this case, we know that we have a weight and bias that needs to be, that they both need to be initialized. And then after that, we can use this nn.init method. And then we can use here normal or Gaussian distribution for the weights, right? So we say nn.init.normal, and we use this for the weight of this layer with mean 0 and a standard deviation 0.01. And then for the bias, it's very common usually to initialize with zeros. And so that's why we use nn.init.zeros. And then we just say that what we want to get initialized with 0, which is the bias term, m.bias. So in this way, you define your function, right? And then after that, you use the name of the network that you have, and then .apply, and then you put the function here. So now you can look at the weight and the bias using what we learned, right? So you can index, for example, the first layer, net0.weight.data, and you can see that we have the weights initialized using Gaussian normal distribution, and the bias term that we wanted to initialize using 0 is also 0, which means that we did this correctly. That's one reason that we make sure always we are able to access the weights and bias terms, right? Because sometimes we want to make sure that if we initialize in certain way, that's actually the case, and that's why it's important to be always able to find these layers and look at these weights and bias terms to make sure that everything is as it's supposed to be. In the last part of this lecture, we talk about how to load and save parameters. This is very important because you may spend a few hours running a model, and you want to make sure that you can reuse this model if you needed tomorrow to make some predictions, right? So you don't want to start this from scratch every single time. And here we again import torch, and then from torch we import nn for neural network. Here also I'm importing from torch.nn functional because I want to use the relu function. So we can either use nn.relu that we have seen before. The other approach is to use the relu from the functional module. And so one nice thing about PyTorch in general is that you can define a class or a blueprint for a neural network. So here we have a class called MLP, and also because we want to inherit properties from the main module that we have here, we use the nn.module. And of course we need to use the constructor, so that's the def and the init. And you can see that we have one hidden layer in this case, where we have 20 input neurons and 256 outputs. And then obviously for the output we have the 256 neurons, and at the end we have 10 neurons. Here the architecture is not really important. We are just looking at how we can store or save and then load these parameter values. And then when you're defining a class or a blueprint for a neural network, you need to also define your forward sort of like operation or forward method, which is this one that we use this self.hidden. We give the input, we use the relu, and then we have the output. And that's like the nice thing about PyTorch, because you don't have to be worried about the backward pass or the back propagation, because that's already inherited from the main module that we have. But the point here is that after you define the class that you want to use for your neural network, you instantiate it. And then let's say here we have some inputs that we want to give, and this is our output, right? And let's say now we want to store or save these parameter values, and that's really easy. You just use torch.save. And that's the other time that you're going to see that we are using this state underscore dictionary, right? So this gives us, if you remember, an ordered dictionary which contains all the parameters, including weights and biases. And when we save these here, and I call it like the name of the network that I have, mlp.params, so that's what it gets saved. And then whenever you want to load this, remember that you cannot store the architecture of the network. The thing that you can store is these weights and biases. So in order to be able to reuse these, you need to again instantiate your object here, which is MLP, and I call this clone, or anything else that you want. And then I use this method called clone.load state dict. And then I just use torch.load, right? So torch.save and torch.load are the main sort of like methods that we use. And now we use sort of like this instance of this class object, and we use load state dict. And as you can see, it says all keys match successfully. It means that we don't have any problems, and we have been able to successfully load all those parameters that we have saved. So this is a very simple case, but in general, you might have a neural network, let's say with 100 hidden layers and so this will definitely be very useful to save and then load these parameters and put it back into your network.